We're going to look here at energy. Specifically, we're going to look at kinetic energy here and kind of how it comes about. If you kind of want to see a derivation of it, that's what this is going to be. So I guess we'll put a derivation. We can get the idea of kinetic energy actually through the idea of work. If we recall from before, we know work is F dot delta x, where remember that dot product represents Fx cosine of theta. We're looking for the parallel components of those forces acting in the same direction. I'm going to assume here, just for argument, that the force and the displacement vector are in the same direction. So our cosine of angle, our theta there is going to be 0, and cosine of 0 is 1. So we're just going to get F delta x here. Technically speaking, that cosine, if you had angles here, would be carried out throughout the scenario, this derivation. But let's just consider it to be 1. Clean up a little bit. Okay, clean up the form of this. So what we're going to have here, in general then, with that cosine going away, we've just got Fx. I am going to recall that one of the greatest equations ever is F equals ma. And if I see an F here and an F here, I'm just going to substitute ma over to the other side. So what we're going to have here is that work is going to equal ma times delta x. Hey, look at that. Work is maximum. I'm also going to recall now, this is kind of a leap of faith, if you will, that when we discussed motion quantities earlier on in the year, there was an equation we had where the final velocity squared was equal to an initial velocity squared plus 2a delta x. That was an equation we had. If you're in the 226, you know that is equation number 6 that we use off of our best friend. But that's just one of our kinematic motion equations. Nothing too crazy there. Well, what I'm going to do here is I'm actually going to solve for delta x. If I solve for delta x here, I'll first subtract this vi squared over, so I get vf squared minus vi squared equals 2a delta x, and then the logical thing to do is divide by 2a, divide by 2a. So what I have here is that delta x now equals vf squared minus vi squared over 2. Oh, you know what? Hold on. Oops. I want to solve for a here. Excuse me. Oh, I don't want to divide by delta, or I don't want to divide by a. I want to divide by delta x. Oops. Delta x. There we go. 2 delta x. And that means that this is an a. Excuse me about that one. We're dividing by delta x's. So now that I have this here, this acceleration is some value that we had from before. Let's just take it and dump it up for the acceleration. So what we'll have now is that our work is going to equal m, and then our acceleration is going to be vf squared minus vi squared over 2 delta x times delta x. And what we see here, this is nice, is that our delta x's are going to divide out. That's what we were trying to do. And if I kind of expand this a little bit, I see that this 2 is in the denominator for both of the velocity terms, and this m, if we wanted to, we could distribute it to both quantities. So what we could, if we wanted to write this out in fullness, we would have this work equals 1/2 m vf squared minus 1/2 m vi squared. So we have this 1/2 mv squared term that's popped up twice here, once for the final, once for the initial velocity. And work is related to that. Now if you think about someone on a wagon or maybe someone on a swing, If they're initially at rest, their initial velocity is 0. When you push them, a force moves them through a displacement and they gain this velocity. So what we're seeing here is that doing some amount of work is changing their velocity. And we know that kinetic energy is the energy of motion. You have this when you have some velocity. So we actually see here that we can define a kinetic energy, K, or some people like to write it KE. That is 1/2 mv squared. And what we can see here in this kind of long equation is that some amount of work being done is equivalent to a change in kinetic energy. And we have this idea of a change, a delta, because we have a final minus an initial. That's the idea of a delta. So what we can actually say here is that if work is equal to F dot delta x, remember there's the dot product there, that's going to equal the change in kinetic energy. And since both kinetic energy terms from above are going to have this 1/2 m associated with them, let's just pull that out, say 1/2 m, and then our velocity terms, vf squared minus vi squared. And this right here, that shows how work is related to kinetic energy and how we can kind of use that. An important thing to recognize is that these squares here, you have to do that before you subtract. If you don't do that, the math works out differently. If you kind of think of this as 3 squared minus 1 squared, well, 3 squared equals 9, 1 squared equals 1, that equals 8. If you do this incorrectly, if you subtract beforehand, if you do like 3 minus 1 squared, that's equivalent to 2 squared, which is 4, and 4 does not equal 8. So make sure that you square first before you subtract these terms out. But this is our work energy theorem here. This is a huge equation. Does a lot of really nice things for us in terms of not having to go through all of our kinematics anymore, not having to use F equals ma for some situations, simply because we've already included them. We included F equals ma up above. We included kinematic equation and substituted it in, and it allows us to get forces and velocities to match up together. So it's a very nice thing there for our work energy equation. We need that, but right there for a derivation, that's finished.